Hello and welcome, Physics 1401. We started solving problems from the force, chapter about force, and today's the second part. I'm just going to keep solving problems from the book, okay? So yesterday we stopped at gravitational forces. I think I solved one problem. Let's pick another one and then move on to contact forces after that. Okay, let's try 56. It says, how far above the surface of Earth does an object have to be in order for it to have the same weight as it would have on the surface of the Moon? Okay, so we're talking about the weight of an object on the Moon, and also weight of the same object where, how far above the surface. So this is Earth. How far above the surface? Right here we have the object of mass m. Let's say it doesn't matter what the mass is. Of course, Earth has also a mass. Let's call it capital M. And the same object, same mass. Mass doesn't change, okay? Mass never changes. Weight changes. So on the Moon, the weight will be different. Okay, it's going to be approximately 1/6 of its weight on Earth, because the value of little g is around 1/6 of the value on Earth, right? Okay, so what is h? If the weight on the Moon is now equal to the force on m over here on the left. Okay, and then this is the same weight. If these two are the same, what is h? All right, so okay, g on the Moon is 1/6 of the g on Earth, our g, and g is approximately 9.8 meters per second square. Okay, that's on the surface. Let's call it the lab frame. Okay, the acceleration due to gravity on the in the lab, that's 9.8 meters per second square. Now we can either use this information here or we can use some astronomical data and just stick with Newton's law of gravitational attraction. Okay, what do I mean by that? We solved this formula last time. If g is equal to capital G times m1 times m2 divided by the square of the separation of the center of masses. All right. So for the Moon case, W, which is the gravitational force, right? Weight is the gravitational force, just becomes this gravitational constant times the Moon's mass. Let's call it m prime. M prime is Moon's mass times this m, that's our object's mass, divided by r. Okay, now that r is approximately equal to the radius of the Moon. Radius of the Moon. Okay, so we square it and write it there. That's W. But the same weight happens over here. Now we have the radius of Earth, of course, RE, plus h. So this is also equal to G times now Earth's mass, capital M, times this test mass, little m, divided by the square of RE, radius of Earth, plus this height that we're looking for, squared. Okay. Now, if these two are to be equal to each other, this means we can cancel G and M right away. So we'll end up with the moon's mass divided by radius of the moon squared equals, what do we have here? Earth's mass divided by radius of Earth plus h squared. Okay, so M prime, M, our moon, and RE can be found either online or somewhere in the book. You just plug them in and solve for h. Okay, actually it's pretty much that. So how do we do that? Let's rearrange this first. RE plus h squared is equal to M over M prime times our moon squared, and then take the square root of both sides. Okay, take the square root of both sides, which will give you RE plus h equals R moon times square root of M divided by M prime. Therefore, h is our moon times square root of M over M prime minus RE. Okay, are we recording? Let me just check if we're recording. We are recording, great. Okay, so let's plug those in. Okay, radius of the moon. Now, radius of the moon is around a quarter of the Earth radius. Okay, we can find the exact number if you Google, but I'm just gonna use this approximation. So radius of the moon is 1/4 of the radius of Earth, which is 6,371 kilometers. Okay, now we need the mass of Earth, and we need to divide that by the mass of the moon. Now these will be in kilograms, and the mass of the Earth is in the order of 10 to the 24th power. And then 10 to the 22nd will be moons, and I need to find those numbers, which I will in a minute, but minus 6,371 kilometers. Okay, so we need now Earth's mass, exact number, and that is 5.97. 5.97. And what about the mass of the moon? The mass of the moon okay, let's look it up. Okay. Moon mass 7.3. Okay, this could be 7.5. Let's say 7.5. 7.5. Okay. I mean, I could look up the radius of the moon as well. It's probably not exactly a quarter of Earth's radius, but it's okay. Doesn't matter. 5.97. Oops. let's write it as 597 and divide it by 7.5, 79.6. Take the square root. Take the square root of that number. 8.9 times 6371 divided by 4. 14,210 minus 6371. So I got 78.39 approximately. That's the altitude. So that's greater than the radius of Earth, as you see. Okay, so that's how we find the altitude, where the object weighs the same as it would weigh on the surface of the moon. All right, okay. So, you want to do another one? Let's do 51, and then we're going to move on to contact forces. 51. It says, what is the approximate magnitude of the gravitational force exerted by the Sun on the Voyager 1 spacecraft when they are separated by 17 billion kilometers? 17 billion kilometers. The spacecraft has a mass of 722 kilograms. Okay, this is the spacecraft Voyager 1. All right, and then what is the force that the Sun exerts on Voyager 1? So we need the mass of the Sun. Okay, I remember this one. This is 2 times 10 to the power 30 kilograms. That's the Sun. All right, so we just need to plug those into our formula. The gravitational force will be then 6 times 6, 7 times 10 to the negative 11. That's the value of G. I'm not writing units to save time. So the masses will be multiplied. 2 times 10 to the 30th times 722 divided by the square of 17 billion kilometers. Now you've got to be careful here. If you want to find the force in newtons, everything has to be in kilograms, meters, and seconds. We don't need seconds here, but we have to convert R to meters. Okay, so 17 billion. Billion means 10 to the power 9, but that's in kilometers. You need an extra 1,000 to multiply that with, and then you get in meters. All right, so this is the distance in meters. All right, 17 trillion meters squared. All right, so let's do 6.67 times 10 to the negative 11 times 2 10 to the power 30th times 722 divided by 17 10 to the power 12 squared, and that is 3.3 times 10 to the negative 4 newtons. Okay, very small. Let's check the answer. 51, chapter 2, 51. 51, 3.3 times 10 to the negative 4th newtons. Okay, well, this problem was simply a plug-in formula. pretty much, okay? So, nothing complicated here. Okay, let's do 61. Maybe that's more interesting. 61. A binary star system consists of two stars of masses m1 and 4m1. A binary star system is just two stars. Okay, most of the stars in the universe are binary stars. Our sun is not. But those two stars have comparable masses, as it is in the case here, m1 and 4m1. If they're comparable in size, instead of one going around the other, like planets do, you know, they actually go around each other like this. Okay, so m1, and then 4m1 is the sister star. So they have a common center somewhere in between. Okay, they go around that center here, let's say over here. And this one like this. That's how they rotate around each other. That's a binary star system. So a distance d apart. D apart, I'm taking that to be from their center of masses. They're d apart. Is there any point where the net gravitational field due to the two stars is 0? If so, where is that point? Okay, so is there any point along that green line? Such a point, if you place a test mass, like a spaceship there, it will be attracted by both stars, but the force would be equal on each side, so it will be canceling each other. That's pretty much what they're asking, okay? So let's do that. Let's place a test mass over here in between. It doesn't matter where you put it. Just pick a distance, call it x, for instance. Okay? But at that point, you place a mass, let's call it little m. Little m. So this little m will be experiencing forces due to these, one to the right and one to the left, or to the smaller star, let's say. Okay, if these forces are equal, that's what they're asking here, you know, that's the point where the net gravitational field due to the two stars is 0. All right, so let's find it. Let's find it. So let me just replicate what I did here. We have a mass, and we have the two forces equal to each other. Okay, let's call it FL, FR, meaning left, R, I mean L for left, R for right, right? Okay, so what is FL, for instance? Use the same formula over and over again. G times the binary star's mass, m1, times our test mass, little m, divided by x squared. Okay, that's the force between m1 and m. That has to be equal to the force on the right, which is g times, now instead of m1, of course I have 4m1. 4m1, that's the mass of the other star, times m, the test mass. Now I need the square of the separation between the test mass and 4m1, the star on the right, and that is d minus x. D minus x, and I'm going to square it. Okay, so what is x? That's our question, right? What is x? That's what they're asking. Just solve this. Solve this for x. Get rid of the g's, get rid of m1, get rid of test mass, m. Now, do we know what d is? They don't give us d. So we're going to find x in terms of d. Find x in terms of d. All right. So we have squares on both sides. Let's take the square root. 1 over x will be equal to square root of 4 is 2 divided by square root d minus x. Or if you cross multiply, d minus x is equal to 2x. Therefore, 3x is equal to d, and x becomes a third of d. All right? A third of d. Okay, so it's got to be closer to the smaller star because you want the gravitational forces to cancel out. Okay, so that's the answer, d over 3. All right, I think that's enough for gravitational force. Let's move on to the next section, contact forces. Okay, let me just clean the canvas. All right, so let's pick a problem from this section. Okay, this also has friction in it. I just read the word friction here. So let's do 71. Let's solve 71. A 3 kilogram block is at rest on a horizontal floor. 3 kilogram block. M is 3 kilograms and at rest. If you push horizontally on the 3 kilogram block with a force of 12 newtons, F 12 newtons, horizontal, it just starts to move. All right. It just starts to move. So any force less than 12 would not be enough to move it. That's how I understand it. Okay, so remember, in the case of friction, you could start with a force less than this 12. Okay, and you could increase gradually that force. And what happens is, the friction force that opposes you, which is between the block and the surface, also increases. So along that line, the friction force, friction F, increases as you increase the force you exert. Up to this point here. And then if you increase more, it's just gonna help accelerating the object. Don't worry about that, but basically after that the friction remains constant, like this. But we're given here that threshold, okay, that 12 newtons. 12 newtons. So along that line, friction force F is equal to the force we apply. Okay, this is little f for friction. Okay, so now let's think about the weight of the object, which is pulling it downward. Weight. And weight is not given, but we're given the mass. We can find the weight from mass. It's just m times g. All right. and the surface exerts a force on the object, which we call the normal force, Fn, which is called the normal force. Normal means 90 degrees, because that force is making an angle of 90 degrees with the surface. All right. So that's it. We have just 4 forces acting on the object. Now this friction force increases as you increase the force that you exert on it. But at this point, you've reached the maximum friction you can get, okay? This is the static phase. It hasn't moved yet. This is the static phase. In the static phase, you can call it Fs if you like. Fs meaning static. This static force has a maximum value, which is this. And that maximum value, let's say Fs max, is related to the normal force. You just multiply the normal force, Fn, by a coefficient called mu, or mu-s in this case, s for static. Okay? That's the coefficient of static friction. So we know that the value here is equal to 12 newtons. What is Fn? All right. Now there is no motion up or down. We have equilibrium in the vertical direction, which means that the weight of the object is equal to the normal force. So this right hand side is nothing but mu-s times normal force, which is mg. All right. So now it's just a problem of solving for mu-s. Mu-s will be equal to 12 newtons divided by mg. What is m? 3 kilograms. And g is 9.8 meters per second square. Okay. Just plug those numbers in. 12 over 3 is 4. And 4 divided by 9.8. 0.408. Let's say, let's just use 2 significant figures, 0.41, let's say. Okay, that's our mu-s. This was part A. Part A, what is mu-s? What about part B? A 7 kilogram block is stacked on top of the 3 kilogram block. Alright, this is 3 kilograms. Now you have another mass, which is 7 kilograms. Alright. What is the magnitude of the force F acting horizontally on the 3 kilogram block as before that is required to make the 2 blocks start to move together? Now what happens when you place that 7 kilogram mass? Okay, you have an object, on top of it you put another object, which pushes this even more, right? So the contact force between the floor and the 3 kilogram mass increases. That's pretty much what it amounts to. So is 12 Newton enough to move the objects now? Probably not. That's what they're asking. So what is that new force, which is going to be greater than 12? All right. So let's place our friction force here again one more time. It's going to oppose us, F, okay. Now we need to find the maximum value of that. because we know that the maximum value is when it starts moving. Okay, you have to at least go to that value when you increase the force. All right, so that's what we do now. Now you can think both m and little m as one object with 10 kilogram mass, right? So that will be giving you the new normal force. But let's also include here what other forces we have here. Now the big M pushes little m downward. That's something to consider if you do a deep analysis. And then there is a normal force or contact force between the two masses as well in the other direction. Okay, actually these two forces are Newtonian pairs, right? And we have capital M's own weight, which is downward, W, we can just call it capital mg. But we're not going to use these forces because we're not interested in the interaction between the two masses. They move together, okay? What we need to know is what happens between the surface and that. So we just need the normal force over there. So all right, this is the normal force we have. Okay, so you can do it two ways. First, like I said, you can simply add 7 and 3 and get 10 and multiply it by 9.8 and you're good to go. Okay, take that Fn, plug it in here. Mu s is 0.41 times that number times 10 times 9.8, 0.41 times 10 times 9.8, 40.2 newtons. Okay. Oh, there's another way. Now you can isolate, if you will, the mass on the bottom. You can isolate this and draw a free body diagram for that. Okay, we have its own weight, which is little m times g. We have the normal force, that is the one above, Fn. And we have the force that the top mass exerts on it. And we haven't given the name, let's call it Ft, F top. And we have the force we exert on it to the right and the friction force to the left. Okay, and you could isolate the top mass as well. In that case, you have its own weight, that is capital mg. You have the normal force from the bottom, call it Fb, Fb, okay? And if that's the static case, if it's not moving yet, pretty much Fb is the only interaction force. If this was in motion, I would include a horizontal component, but it's not, so we can ignore it. We just have two forces. Okay, FB is the small mass exerting on the bigger mass, and mg is its own weight. So obviously, using Newton's third law, FB in magnitude is equal to Ft, which is mg. Alright, so you take that mg, which is equal to Ft, and plug it in here to find Fn. So Fn must be equal to Ft plus little m g. So this is going to be plugged in here, mg plus mg, and you get m plus m times g. Okay, so that's where it comes from. If you want to do it like that, no problem. Or if you just want to skip all that stuff and write this, and that's because now you're thinking the two masses as a single system, as if they were glued, okay? Which is not a bad approximation for this part of the problem. If this was in motion, that's a different story. Okay, then you have to include horizontal forces. Okay, so you can take the shortcut and simply add 7 to 3 and get the 10 kilogram and multiply it by 9.8 to get the normal force, and that times 0.41. See, 0.41 is the coefficient that doesn't change just because you add another mass. Coefficient has to do with the material, okay? So it has nothing to do with the mass above. It just has to do with what it's made of and things like that. Okay, so the answer to part B is 40.2 newtons. Okay, this was 71. Let's check the answer. It's an odd numbered problem. We can check the answers to make sure we did it right. Chapter 2, 71. 0.41 and 40 newtons. Good. Okay, so you want to do one more? One more contact force problem? This was 71. Let's do one more. Which one? Let's do the last one. 78. You are pulling a suitcase through the airport at a constant speed by exerting a force of 25 newtons at an angle 30 degrees from the vertical. Something like this, okay? So that's 25 newtons. The angle it makes with the horizontal is 30 degrees. All right, so constant speed, that's the key here, constant speed. Now you got to remember Newton's first law from last week, right? Newton's first law states that if the net force on the object is 0, it's going to continue moving along a straight line. In other words, the velocity will not change. Okay? It may not move at all, that's another option, but after all, motion is all relative. You can always find a frame where it's not moving, right? But the key is being constant. Speed is constant. Now, note here, constant speed does not always mean 0 net force. Let's say you're on a highway, okay, I-10, and then you want to make a turn to 290 or 610, okay? So you take a curve, and your speedometer, your car speedometer may show the same number, 35 miles per hour. So your speed is not changing, but your direction is changing because you're making a turn. Now that counts as a change in velocity, okay? So you're not in the realm of Newton's first law anymore, or you can say Newton's first law says that there must be a force acting on it, net force. Okay, so constant velocity means zero net force. Constant speed, you have to look at the path. Is it a straight line? If it is a straight line, as it is in this case, yeah, it's fine. But if it's a curve, that's no longer a zero net force situation. All right. So what is the question? The question is, what is the force of friction acting on the suitcase? Of course, there has to be a friction force, otherwise there would be nothing to compensate for F, right? So let's include that. The friction force will be in the opposite direction. If things are in motion, the friction force is always in the direction that opposes motion, okay? If it's moving to the right, friction force should be to the left. Is that it? No, there are two more forces, right? We have the blocks, the suitcase's own weight, which is its mass times acceleration due to gravity. And we also have the normal force. The normal force, okay? So, these are the four forces. These should add up to zero. That's why it's going to move with constant speed, okay? F net should be zero. And remember, it's a vector equation. Means there's an x component to it and there's a y component, or horizontal and vertical, if you will. X component and y component to this equation. So F net x is 0. F net y is also 0. Okay, so I'm not going to draw a separate free body diagram because I already have all the forces now. I'm just going to show the components of F. In addition to this, let's use green. If you draw a box around F, okay, you will recognize these sides as the component vectors. Okay, so this will be Fx, this will be Fy. So let's take the first equation and along the x direction. If F net x is 0, this means I have to consider everything along the x direction. What do I have? I have two forces, Fx to the right, pointing to the right, and F pointing to the left. I can say Fx is equal to F in this case, or if I want to write it as similar here, in a similar fashion, I can write minus F, meaning it's pointing to the left. So Fx minus little f, and this is F is the kinetic friction force in this case. I can put a k there to separate it from static. Fx minus Fk is equal to 0. Now what about the equation in the y direction? Well, I have 1, 2, 3. Alright, I have the normal force pointing up. I have Fy, the y component of F, pointing up, and mg pointing downward. I'm going to subtract it from the rest, is equal to 0. Okay? Alright, I can find Fx and Fy. It's just a matter of cosine and sine, so no problem there. I know those two. M, do I know M? I don't know M. Do I know Fk? I know how to write Fk in terms of M. Okay? This is the kinetic friction force. That will be equal to the kinetic coefficient of friction times the normal force. Alright, so that's how I relate. I have three equations. which I need to solve for force of friction. Okay, so let's use all that information and solve the problem. Let's start with fx, that is 25 cosine 30. Okay, minus fk, which is mu k, times fn. And that's 0. Actually, this equation itself just gives me the friction force right away. Okay, I don't even have to worry about the rest. Right? I don't even have to worry about the rest. So this is the friction force. So the friction force, kinetic friction force, is 25 cosine 30. .65, let's say 22 newtons. Okay, well, what about the other two? I mean, this equation, for instance, can I do anything with it? Well, I mean, we already found the solution, but let's play with it to see where it takes us. So, 25 cosine 30, that's 22. Well, let's use the exact number for now, 21.65. 21.65 minus mu k Fn equals 0. Now, Fn over here in the second equation plus Fy, and that would be 25 sine 30. Sine 30 is 0.5, so it is 12.5. Okay, 25 times sine 30 is 12.5 minus mg. G is 9.8. Equals 0. Okay, I mean, I have three unknowns basically, Fn, m, and mu k, and I only have two equations, so that's pretty much it. Okay, we can't do anything more than that. All right, so if one of these unknowns were given, we could find the rest, but we don't have it. So there's your answer, 22 newtons. Okay, next section. Or do you want to do one more? Ramp. There's a let's do 64. That looks interesting. Let's clean it. 64. A box sits on a horizontal wooden ramp. Okay. A box sits on a horizontal wooden ramp. The coefficient of static friction between the box and the ramp, mu s, is 0.3. Okay, this is between the box and the surface, wooden ramp. Okay, you grab one end of the ramp and slowly lift it up, keeping the other end of the ramp on the ground. So let's keep this end on the ground and lift this side up. So now we do it gradually or slowly. Let's say we're here now. I guess the box has not moved yet. That's what they're saying. So Okay, so we're lifting it. What is the angle between the ramp and the horizontal direction when the box begins to slide down the ramp? Okay, so they're looking for this angle now. Theta. So theta increases and then the box starts sliding at one point. So what is the maximum angle that we have to have, right? What is the maximum angle allowed? And below that, the box will not be moving, okay? So it all comes down to that picture that I drew earlier. The horizontal force versus the friction force. This is the breaking point. This is the static phase. And after that, it becomes kinetic. So we're after right here, okay? What we want to find this maximum value of the static friction force, Fs max. All right, now this one's interesting because we have now an inclined plane. An inclined plane, okay? And what are the forces here? There's gravity pulling the object downward. mg. We're not given m, but let's just keep it as mg for now. Now, the thing that keeps it from sliding down is an upward, or up the slide, up the incline, friction force, right? So it's got to be this way. This is the friction force. Fs. Okay? Now, this picture is when theta is less than that critical value of theta. It's not moving yet. Okay? But our goal is to find the critical. So when the horizontal force, not horizontal, when the force along the incline is equal to the maximum available friction force, that's when you hit the critical angle. Okay, so what is missing here? The normal force is missing. Let's place the normal force. By definition, it has to be 90 degrees. Normal means 90. So it's 90 degrees to the surface. That's Fn. Alright? So, let's draw a free body diagram for this one, okay? Now, a free body diagram, just up to you. You can draw it in any way you like, as long as you only show the external forces. And it's convenient in this type of problem to use a rotated coordinate frame. I'm talking about the x, y's, okay? So you can place your x in this direction. Okay? So this is your x, and this is your y. The advantage of doing it like this is, well, except for mg, all the forces line up with the axes. That's the advantage. So mg is downward. And Fn is along the y-axis. And Fs is along the x-axis. Now, what is the angle that mg makes with the y-axis? I mean this angle here. That is equal to theta. Y, well, if you go back to the original picture here, if you extend this line, which we accepted as y, like this, okay? So this is theta. What is this angle? That's what we're trying to find, right? Now this is 90 degrees right here, which makes the angle right above it, over here, 90 minus theta. 90 minus theta. All right. Okay, so if this line is parallel to the x-axis here, it means this is also 90 minus theta. But y is perpendicular to x, so the complementary angle, I think that's what you call it, right? The angle we're looking for. When you add it to 90 minus theta, you should get 90 degrees again. So this makes it theta. That's why I call this theta. So that's our free body diagram. And there's no movement, so I'm not going to put any acceleration there. How do we write down the equations, equilibrium equations? Okay, let's do that in the x and y directions again. So along the x direction and along the y direction. Now Fs lies along the x, just write it there, Fs. Fn has nothing to do with x, but mg does have an x component. Draw your box around mg and see where your x is. It's right here. That is the x component of mg. And along the y you have this. This is the y component of mg. Alright? Now the y component of mg has a magnitude of mg times cosine theta. Why? Because I have a right triangle here. Here's the right angle. Similarly, if I consider the opposite side to theta, that's where you have your x component. So it is mg sine theta. Okay? I mean, they're pointing in the negative y and negative x axis, which I'm going to take into account. But the length of those sides are mg cosine theta and mg sine theta. So in this equation for x, now I need the other side, which is mg sine theta, minus, because it's pointing in the negative x direction, minus mg sine theta. And that's equal to 0. Okay, now what about the y direction? I have Fn upward, or in the positive y direction, and I have mg cosine theta in the negative y direction. Okay. Now, you got to be careful here. Fs is not equal to mu s times Fn in general. Fs is simply equal to mg times sine theta. It depends on what theta is. If theta is less than that critical value, Fs is, it can be anything. It has nothing to do with the normal force. But only when we're at the critical angle, the maximum friction force, right, maximum static friction force, that value is equal to mu s times normal force. Okay, so only when Fs is equal to Fs max, when you reach that value, is equal to mu s times Fn. And that's indeed what we're trying to find. Okay, so these equations are generic. I mean, they hold for any angle between 0 and the critical angle. They just come from this. F net is equal to 0. That's the condition for equilibrium, right? Equilibrium. But when we impose this condition over this, if that's the case, then we can say Fs is this number. So mu s times Fn, okay, minus mg sine of that critical angle. Let's call it theta c critical equals 0. Similarly, the second equation reads Fn minus mg cosine theta critical equals 0. Okay? So, what do we know here? We know the value of mu s. It's given. It's 0.3. Good. That's the only thing we know pretty much. From this, we got to be able to solve for theta c. So given mu s equal to 0.3, what is theta critical? We don't know m, we don't know Fn, but no problem, we can get rid of them. How? Well, let's rewrite this equation as mu s Fn equals mg sine theta c, and Fn equals mg cosine theta c. And then divide both sides of the first equation by Fn, let's say. Okay, so we have the first equation, mu s Fn divided by Fn. On the right, we have mu s Fn equal to mg sine theta c. You're dividing it by Fn. Dividing both sides of an equation by the same thing doesn't change anything. But we know that the second equation tells us that Fn is equal to mg cosine theta c. So we just keep writing mg sine theta c. Instead of Fn, I'm going to write mg cosine theta c. Now what happens if I just look at this side and this side? Okay, Fn's cancel, m's go away, g's go away. What is left? Sine over cosine, and that's by definition tangent. Tangent theta critical. So tangent theta critical is equal to mu s, then theta critical is equal to arctangent of mu s. All right? So my calculator is set to degrees, just fine. Arctangent of 0.3, that is 16.69, close to 17 degrees. All right, so that is the, what number was this? That is 64. Okay, next section about tension. Let's solve a couple of tension problems. All right. Let's do the first one, 79. Spring scale A is attached to the floor. What is a spring scale? You know what spring is, right? You take a piece of wire and you wrap it around a cylindrical, like a pencil or something. So you take a piece of wire and wrap it around some cylindrical object and take it out. You have your spring, right? And what can you do with springs? You can stretch them or you can compress them. Ideally. Well, some springs you can only stretch. Some springs you can only, well, the ones in your mechanical pencil, okay, they're already been compressed or near compression, and then you just compress them, okay? But the spring under your car work both ways, okay? So you may have different ways, but ideal springs in this book, in this physics, okay, is the one you can stretch or compress. And when you do it, the amount of stretch is proportional to the force you exert. All right, so it means that you exert a force and you stretch it all the way to here, and now it is this much from the away from the unstretched position, let's say. You exert a force F. If you double the force, what happens? This distance also doubles, okay? That's an ideal spring. So within a certain range, if you stretch it too much, okay, it deforms and then it doesn't work anymore. But you can use this to make a scale. That's what they're talking about, a spring scale, okay? So you can place this in a frame, and then maybe an extension here, and then you can add some scale here, which shows you what the force is, okay? A spring scale. So spring scale A is attached to the floor, and the rope runs vertically upward, loops over an ideal pulley. Let me just draw the picture here. So we have a pulley attached to the a spring attached to the ceiling, a spring scale attached to the ceiling, and you hang a pulley. A pulley, okay? So the pulley has a frame. That's where you attach it. Over the pulley you have a rope. And one side is tied to a mass. Its weight is 120 newtons. Okay, and then the other end is connected to another spring scale. This one is B, this is A, it says. And the scale is attached to the floor. Okay, so we have the forces in the spring scales which make them stretch, and we have a force inside the cable which we call tension. That's what this section is about. And we have the weight on the right, which is 120 newtons. What are the readings of the two spring scales, A and B? In other words, what are the forces there, okay? Ignore the weights of the rope, pulley, and scales. Okay, so why don't we draw a free body diagram? Draw a free body diagram for what? Well, we have the scales, we have the pulley, we have the weight. Let's start with the weight. So I'm going to isolate the weight here and draw a free body diagram for that weight only. Okay, so what are the external forces acting on the weight there? Earth pulling it downward with a force equal to W, 120 newtons. And this cable pulling it upward. I'm going to call it tension, or T. That's pretty much it, okay? Those are the only forces acting on the weight. And if this is an equilibrium, it means that T minus W is equal to 0. In other words, T is equal to W, which is 120 newtons. Now let me repeat it for the pulley. Let's draw a free body diagram for the pulley. Let's isolate it, okay? Imaginary scissors you cut the ropes and the scales and everything, you just take it out. That's what I mean by isolation. And this way you can write the forces. Show the forces acting on the object. This is for the pulley. Okay? Now the pulley is experiencing actually 3 forces that I have to show. The spring scale is attached to it. It's actually pulling it upward. So I need to place an arrow here that stands for the spring scale B. Let me call it FB. Alright? Now, the point of isolating this here is I don't have to worry about the weight or the spring anymore, because remember, the spring here is not directly attached to the pulley, it's only attached to the rope here. Okay? So once I isolate it, I can get rid of the spring scale A and the weight, but I have to replace them with something. What is in contact with the pulley? The string, the cable, the tension. That's what I need to include, right? So the tension here, remember the double arrows I mentioned earlier? To show tension, you use double arrows. That's the idea behind it, okay? You put 2 arrows here, meaning that when you isolate the separate objects, you can always take the tension to be a force which is away from the object. So basically I have 1 here, another 1 there. I have 2 T's, tension, pulling it downward. T and another 1. Alright? So that's it. I only have 3 forces because they told me to ignore the weight of the pulley itself. I'm not considering that. So what is the equilibrium equation then? FB minus T, which is 2 T's, equal to 0. Okay. So let's do it for spring A. Let's do the same thing for spring A. Meaning, draw a free body diagram. This is the spring scale A. Right? Now the spring scale, if you look carefully in the picture, is attached to ropes. Okay, so attached to the upper rope. Now we don't really have to worry about the bottom because I don't want to introduce another T there. I'm just gonna call it FA. Okay, so FA, and I have T here. Okay, basically the arrow up here, this arrow, is what I include in the free body diagram. And the force in the spring, FA, I just put it over here. Okay, so the equilibrium condition is then that FA is equal to T. And FB is equal to 2T. 2 T's. And what is T? T is 120. So FA is 120 newtons. FB will be 240 newtons. Okay, I think this was simple. Let's do another one. Let's do 84. There's a nice picture there. Let's do 84. Are we recording? Recording, right. A 200 Newton sign is suspended from a horizontal strut of negligible weight. I'm just going to draw the picture and read it after that. There's a wall here, and the strut they're talking about is just some, I don't know, a rod or piece of wood, you know, strut. And then you hang a sign. This is the sign, and it's 200 newtons. Okay, the force exerted on the strut by the wall is horizontal. Let's use red. The force exerted on the strut by the wall, F, is horizontal. Okay. And there is a cable supporting the strut. The cable supports the strut like this. The cable is attached to the strut. Find the tension in the diagonal cable supporting the strut and the angle it makes with the strut is 30 degrees. Okay, so we need to draw a free body diagram. For what? For the object, for the wall, for the rope, for the strut? Let's do it for the strut. Okay, so now if you want to do it the same way we did before, you can isolate the object first, imagining, you know, there's a little chain there that connects the strut to the sign, and then consider the tension in that chain and all that, but that's going to be equal to 200 newtons anyways. Okay, so there's no harm in just using 200 newtons directly. You know, you can just do that. You can just do that. Okay, so I'm just going to skip that step, let's say. So let's include that as a downward force and done with it. Okay, this is W, weight 200 newtons. Now, do we know the weight of the strut? Negligible weight. Okay, so we're ignoring the weight of the strut. Ignore the weight of the strut. Good. So what else do we have? We have F, that horizontal force the wall exerts on the strut. It's pushing it to the right, which I just called F. Fine. F is not given, and T is not given. We're supposed to find that, right? So let's just show T as well here. That's T at 30 degrees. All right, that's all. That's pretty much it. So that's an equilibrium. Then the forces in the x and y directions should be canceling each other. In other words, F net is 0, means F net x is 0, and F net y. The x and y components of F net are 0. All right? So in the x direction, what do I have? I have this F here, the force that the wall the force the wall exerts on the strut. W has nothing to do with what's happening in the x direction. But T, on the other hand, has a component. It has an x component. It also has a y component. The x component is given by the cosine of 30. So T cosine 30. And similarly, the y component will be T sine 30. Why? Because this side is equal to that side opposite to 30, right? That's why. Good. So let's include T cosine 30 in this equation. F net is the net force, so F to the right, T cosine 30 to the left, therefore minus T cosine 30 is equal to 0. Okay, good. What about the y direction? We have T sine 30 up, and we have 200 down. 200 newtons down, so therefore negative. All right, so that's it. That's it. Those are the two equations. Now, we have two unknowns, right? Two unknowns, and they don't even ask what F is. So pretty much all we have to do is take the second equation here and solve for T. 200 newtons divided by sine 30, and that is 400 newtons. If they ask F, you can just take that T and plug it in the first equation and solve for F. All right, so that was it. Let's do 86. Okay, a crow perches on a clothesline midway between two poles. Okay, let's see if I can draw a bird here. Two poles. Normally the clothesline, the rope would be over here, stretched, but now the bird is sitting in the middle, I guess. Midway, yeah. It's a little bit of an exaggeration, I guess, but that's pretty much where the bird sits. Okay. Okay, that's as good as it gets. Okay, that's the bird. Each end of the rope makes an angle of theta below the horizontal. Where it connects to the pole. If the weight of the crow is W, what is the tension in the rope? Ignore the weight of the rope. The tension, okay? So the tension is equal on both sides. It's equal to T. Okay. I mean, I keep using that double arrow notation. I hope that doesn't confuse you. It's just a habit of mine. But if I draw a free body diagram, I don't need to include that. A free body diagram for this point here where the bird sits, or the bird itself, let's say. So okay, so what are the forces there? We have the weight pulling it downward. We have tension on one side pulling it like this, and the same tension pulling it like that on the other side. And using symmetry, if you consider a line here parallel to the clothesline, original position of the clothesline, two parallel lines and intersecting lines, you will see that this is also theta here, and this angle is also theta. Okay, these are theta. All right, so how do we find t? And theta is not given. All right. Okay, so we have equilibrium. The net force should be 0. Along the x direction, we have t cosine theta to the right and t cosine theta to the left. Right? These two have components. This is t cosine theta, t cosine theta. They just cancel out each other. Okay, so nothing exciting happening in the x direction. What's happening in the y direction? Now those t's have these components. These arrows are the component vectors of each tension on right and left sides. They cannot cancel each other. They're both pointing up. We have to add them actually. So this side is t sine theta. Okay, t is nothing but the hypotenuse. So the side opposite is t sine theta. We have two of those. So t 2t sine theta must be the sum of the y components of tensions, and downward is w minus w is equal to 0. So solve for what are we doing? Solve for t. Solve for t. Okay. Take the second equation. And solve it for t. Okay. Move a w on the other side and divide both sides by 2 sine theta. That gives you tension. So how are we doing on time? It's been 1.5 hours. Okay, I don't want to have a part 3, so let's just keep going, okay? Okay, I mean, I don't know what else to say about this problem. It's really that. We drew the free body diagram. T cosine theta, T sine theta. We're told to ignore the weight of the rope itself. Okay, we just did that. Yeah. Let's do 87. Okay, there's a picture again. A 2-kilogram ball tied to a string fixed to the ceiling is pulled to one side by a force F. So here's the ceiling. And you tie a string, and the other end of the string is tied to a mass, a ball, of 2 kilogram mass. And it's pulled to the right horizontally with a force equal to F. And the angle the rope makes with the horizontal, or the ceiling, is 30 degrees. Just before the ball is released and allowed to swing back and forth, okay, how large is the force that is holding the ball in position? Okay, and what is the tension in the string? Find F and find the tension in the string. Okie doke. So, free body diagram. For what? For the ball. Draw a free body diagram for the ball. And let these be the X and Y coordinates. Now, the ball has a weight, which we always show, and it's always pointing downward, okay? Please make sure you keep the same when you do your problems, and don't show the weight pointing in different directions, okay? Just show it downward. mg. F, on the other hand, is to the right, and T is here. Okay. T never is into the object. It's always outward, going away from the object. And the angle it makes with the horizontal, this angle I'm talking about, is nothing but 30 degrees. This is 30 degrees. All right, so F holds the ball in position. Let's find it. Now, equilibrium states that F minus T cosine 30 must be equal to 0, and also T sine 30 minus mg must be equal to also 0. Now, n is known. What are the unknowns? F and T. And how many equations do we have? 2. So this should be solvable, right? Let's start with solving T. T is equal to mg over sine 30. Okay, so m is 2. G is 9.8. Meters per second square. So that gives me what? 19.6. And you divide it by 0.5. Pretty much that's what we're doing here. So you're multiplying it by 2 in a way. So 4 times 9.8, 39.2 newtons. And take that and plug it in the first equation, which will give you F now. T cosine 30. So 39.2 newtons times cosine 30 times cosine 30, that is 33.9. 33.948, that's gonna become around 34 newtons. Okay. Now, Is that the only way to solve these two equations? Like part A is find F, part B is find T. I first found T and then found F. Maybe you want to first find F, because that's part A. You want to do part A first and then part B. What are you going to do then? Okay? Or, let's say, or we take these two equations, but solve for F first. How do we do that? Easy. You can write them as T sine 30 is equal to mg. That's the second equation. And the first equation says T cosine 30 is equal to F. Okay, and then same thing. Divide the first equation by F. F is T cosine 30, so you have T sine 30 over T cosine 30, which is T's go away, and you have tangent. Tangent 30 is equal to mg over F. In other words, F is equal to mg over tangent 30. M is 2, g is 9.8, divided by tangent 30. Okay, so 19.6 divided by tangent 30, 33.9, which we wrote as 34 newtons. And you can take that F and plug it in the second equation. Then T is equal to F over cosine theta, 34 newtons over cosine 30. 34 divided by cosine 30. 34 or 33.9. Okay, and that gives you 39.2 newtons. Okay, so either way is correct. All right, what else? Let's do 96. 96. There's a picture here of someone holding a book against a wall. Not a book, a frame. While trying to decide where to hang a framed picture, you press it against the wall to keep it from falling. So here's the picture. Here's the wall. And here's the frame you're holding against the wall. Okay, and you're using your hand to do that. I'm going to draw a terrible hand now. Okay, that's your hand. All right, and of course you have to press. So you exert a force, right? Let's show that force with what color? Blue. This is the force you exert on the frame. And that's at an angle of 40 degrees. Okay, so that's the picture, and we call it F. Let's read it. The picture weighs 5 newtons. Weight of the picture. Okay, why don't I just show it as an arrow also? Weight of the picture is pulling it downward. Weight. How much is it? 5 newtons. And you press against the flat frame, blah, blah. Okay, we did that. With a force equal to 6 newton. Okay, the F is 6 newtons. At an angle of 40 degrees from the vertical. A. What is the direction of the normal force exerted on the picture by your hand? The normal force. So pretty much it's normal means perpendicular, remember? So we're talking about the component of this F, which is horizontal. So if you draw a box around F, it's got two components, right? A vertical component and a horizontal component. Now, if I were to draw a free body diagram for the frame, this is the frame here. You know, I'm just showing you alternative ways of drawing it. This F I could simply place here like that, and then these components, let's call them Fx and Fy, okay, would be here, Fx and Fy, and this angle here. Now if this is 40, what is this one? That is 50, right? This is 50 degrees. Okay, so what they mean by the normal force is nothing but Fx, right? That's the normal force you exert on the book, not the normal force between the book and not the book, the frame and the wall. That's a different story. Okay. Actually, let's show that in the other direction. Fn. Fn means wall pushes the frame to the left. That's the normal force we're talking about, right? The wall pushes the frame to the left. Well, of course, in return, the frame pushes the wall to the right, but let's not even bother with that, especially when drawing a free body diagram for the frame only. We don't show that. We only show the forces acting on the object. Well, if you want to complete it, you have to also include the weight, which is downward. But there's one thing more, and that is the friction, actually. Well, friction may or may not be there. It depends on the force you exert and the value of Fy. Now imagine, in this case, actually there's no need to imagine. You are given the numbers. You can just find Fy and see how much it is. But in general, when you're holding something against the wall, it just depends on how much force you exert on it, okay? I'm talking about the friction between the frame and the wall. It may not even be present if you hold it with just enough force there, okay? But other than that, you may have a force downward or upward. You know, the friction force may have a direction downward or upward. It just depends on the force you push it with. Now in this case, we are given exactly, it's 6 newtons, so it's not really a thing about guessing. We can just find it out. Let's see, Fy is what? 6 times 6 newtons times sine 50, right? Sine 50. 6 sine 50. 4.59. 4.6, let's call it 4.6 newtons. So is 4.6 greater or less than 5? Less than 5, right? But the frame is not moving, you're holding it at place. So something is actually helping you to keep the frame there. You're pushing it practically with a force equal to 4.6 newtons in an upward direction. But the weight is greater than that. That is 5 newtons. So there's a 0.4 newton difference. And that is from the friction between the frame and the wall. So I'm going to include that in the free body diagram. Let's use blue. An upward force of friction. And friction has to be equal to, 5 minus 4.6 equal to 0.4 newtons. Okay, What about Fx? I think that's what they were asking in the beginning. So part A was Fx, and that is 6 newtons times cosine 50. 6 cosine 50. That is 3.856, 3.9 newtons. And that's part A. Part B, what is the direction of the normal force exerted on the picture by the wall? It's to the left. We already took care of that. This is part B. Part C, what is the minimum coefficient of static friction between the wall and the picture? Okay, now we know what the friction force is. Okay, that is 0.4 newtons. But how do we get the minimum coefficient of static friction between the wall and the picture? Now, this is again about the that picture that I drew earlier. I'm not going to draw it again, but we had this value here, which was F static maximum is equal to mu s times Fn, right? Fn. So that's what we're going to use here, okay? That's what we're going to use. Now, what is Fn? We need Fn, obviously. Okay, Fn is the force that the wall exerts on the frame. And the frame exerts a force on the wall, and the hand exerts a force on the frame. What we drew here was only for the frame, and the horizontal forces are Fx and Fn. So that's it. Fn is Fx. Fn is Fx, which is equal to 3.9 newtons. And we know the friction force. So if we're on the verge of sliding, that would be Fs max, right? So on the verge of sliding means without changing the force, I mean, you cannot really change the value of mu anyways. I mean, it's just the way they ask the question. They say, what is the minimum coefficient of static friction? As if it is something we can play with. No, we can't. We can only change the force we apply on the frame. But imagine a situation where you could really change the friction. Let's say it's really cold and there's humidity, and then suddenly water freezes around it, and then it reduces the coefficient of friction. Something exotic like this, okay? If you want to think like that. But mathematically, what we're really considering here is it's on the verge of sliding. So that critical value is what we are investigating here. So there's no harm in just taking this friction force as that critical friction force or maximum friction force and use that in our formula. Formula meaning this one here I just wrote over here. Okay. So I'm going to divide that friction force by the normal force to get the mu s or mu s minimum in that sense. Okay. So that is equal to 0.4 newtons divided by 3.9. Okay, that's going to be really small, close to, yeah, but let's find the exact number, 3.9. 0.102. Or just stick with the first, the two significant figures, 0.1. Okay, so that is the coefficient of static friction. Depending, that was part C. Part D says, depending on the magnitude of the force you exert, like I was explaining, the frictional force exerted on the picture by the wall could have either of the two possible directions. Actually, I talked about it, but let me explain in detail now, and I'm going to finish there. So, in this case, friction force was upward, and the only reason it was upward was because I looked at Fy and found it to be 4.6 newtons. That was less than 5 newtons, which was the weight of the frame, and I concluded that F has to be upward. If the force I exerted was greater than 6, what if I was exerting, 8 newtons? Okay, let's do it. 8 times sine 50 is 6.1, and 6.1 is greater than 5. So the weight is pulling it down, but it's not enough to compensate for my push, which is 6.1. In that case, the friction force will be downward. Okay, so the friction force, when you hold it right there, the friction force will be downward instead of upward. So it just depends on the force I exert. If I increase the force, the friction force is downward. If I decrease the force I exert, the friction force wants to help me to keep the object in place, and it's upward. Can I get rid of the friction force altogether? Yeah, I can. If the weight is equal to F sine 50, there is no friction needed. Okay, you can even find that force easily. Just equate F sine 50 to weight, which is 5, and solve for F. You can do that. 5 divided by sine 50. So if you're exerting 6.5 newtons instead of 6, there won't even be any friction force. Okay? So that's the thing about static friction force, okay? It's not a fixed amount. The only time you can use a formula instead of the free body diagram to find the static friction force is when you're at the critical point. It's on the verge of sliding, okay? You've reached the maximum friction force. And then you can use this formula. Any other scenario has to be analyzed in detail, and you have to draw the free body diagram and see what forces are keeping the object in balance. Because these are equilibrium cases, static. If the object is in motion, totally different story. If the object is in motion, then you have the kinetic phase, and the kinetic friction force is simply equal to mu k times Fn, always, okay? It doesn't change. No matter how hard you push it, the friction you'll experience is the same. If the object is moving, that's just mu k times Fn. If the object is not moving, the friction you experience changes. It may change direction, as you see in this problem. It may even be 0. Okay? So I'm going to stop here. And next topic is acceleration and Newton's second law of motion. So till next time, goodbye.